So hello everyone, myself Mullah Soel and I'm from Minerva. So today we are going to start with some problems of relation and function. So before this one we have 2 or 3 classes, and in those 2 and 3 classes we covered the portion relation and function. So from now on, today's class will be all about problems. Now we'll learn to solve different types of problems of this chapter. So the first question which we have in here is, show that the relation R in the set A 1 to 3 given by, that's the relation that is given 1 1 2 2 3 3 1 2 2 3, is reflexive but neither symmetric nor transitive. So we have to prove this thing. So first thing, in order to prove, I need to, what should I say, we need to go back to the time where we learned this reflexive, symmetric and transitive. So what was reflexive? So reflexive was what? If I have an element A which is element of a set A, right? Now if I have relation in the set A, so A comma A has to be an element of R. And what is this R? R is nothing but the relation among the elements of set A. So A comma A has to be an element of R. Then we can say that the relation is reflexive. So now look at the question, look at the relation that's given in here. So the solution, what I will start with, so I will write relation is given by 1 comma 1, 2 comma 2, 3 comma 3, and we have 1 comma 2 and 2 comma 3. So by looking at the question, what do we see is that 1 comma 1, 2 comma 2, 3 comma 3, all of these 3 elements of this relation R satisfy the condition of reflexive, A comma A element of R, right? So the relation is reflexive. So write down, since A comma A is an element of R for all X element of A, so the relation is reflexive. So this is my first stage of my proof. Now the next thing, but neither symmetric nor transitive. Now in order to prove that the relation is not symmetric, I need to know what was the condition for symmetric. So for symmetric, if I say A and B are 2 elements of the set A, if A comma B element of A implies that B comma A element of, this one won't be A, it will be R. It will be the relation A comma B element of R implies that B comma A element of R, then we can say that the relation is symmetric. Combining these two, then we can say the relation to be symmetric, right? So here you look at here, now you see whether this relation is symmetric or not. Now in order to prove something, a relation is not symmetric, all we need to do is pick one element which does not follow the criteria of symmetric, and the whole system will fall. It's like that. If I have one problem in there, so I will think of that the whole relation is a problem. One condition which meets the condition of not symmetric, then the entire relation is not symmetric. So look at here, the element 1 comma 2, A comma B is here, but 2 comma 1 is not in here. So this condition, the symmetric condition, is not followed. Acha, fine, this one is okay. Now look at 2 3 also. 2 3 is there, but 3 2 is not there. So both the elements of this relation R does not have its counterparts, that is 2 comma 1 is not there and 3 comma 2 is not there. So what we can say, that the relation is not symmetric. So how will I write that thing? So write down, since 1 comma 2 element of R does not imply 2 comma 1 element of R, so the relation is not symmetric. Now the last one. Now how we need to prove the transitive one? So in order to know transitive, first we need to know what is the condition that is followed by transition. So in transition, I will pick 3 elements. So let us say A, B, C. They are element of the set A, right? Now the condition for transitive is if A comma B is an element of R, and it's not implies, it's and B comma C is an element of R, both these conditions has to be satisfied, then I will check. Both these condition implies that A comma C element of R. If this thing is true, then we can say that the relation is transitive. Again the same thing, one element you take and that does not satisfy the condition of transitive, the whole entire thing is not transitive. So let us see here, 1 comma 2 is here, so A comma B is here, and 2 comma 3 is there, so B comma C is also in there, B comma C is also in there, right? So we need to search for A comma C. So A comma C will be what? 1 comma 3, but I don't see 1 comma 3 in here. So once I don't see 1 comma 3, I can directly conclude that the relation is not transitive. So let's write it down. So I will say that since 1 comma 2 element of R and 2 comma 3 element of R does not imply 1 comma 3 element of R, so the relation R is not transitive. So that's how we prove these type of questions. Okay, so now we are going to start with this new question, the second question of the day. So what do we have in here? Find the domain and range of the relation R. So that's the question. The question ends there. It's just so small a question. So we just need to find the domain and range. So before discussing about domain and range, about this question, first thing we need to know what is domain. Domain is what? Domain means all the, listen very carefully, this thing about definition of domain you will not find in your books. So domain, the definition of domain is all the possible values of x, all the possible values of x for which the function is defined. But you will be asking, sir, here we are doing relation. Okay, so we don't have to bother about that defined thing. So look at here, the relation is given. The elements are A comma B. We generally used to do A comma B and the relation between the elements are given. Suppose it was like this, A is equal to 1 by B. A comma B colon A is equal to 1 by B. But they have included the relation in that ordered pairs only. They have directly said x comma 1 by x. So in here only they have told you the relation between the elements, and they said that x lies between 1 and 10 and x is a natural number. So if x is a natural number, so x will start from where? It will start from 2. So let us draw this one. Let us draw the arrow diagram. Let us draw that one. So if I draw the arrow diagram, how will it look? The first element, the first natural number what we see is, it will be 2, then 3, then 4, 5, 6, 7, 8, 9. It won't be 10. Then x comma 1 by x. So x is my element that will be mapped with 1 by x. So 2 is my element that will be mapped with 1 by 2. 3 is an element, 3 will be mapped with 1 by 3. 4 will be mapped with 1 by 4. So like this way it will go, and 9 will be mapped with 1 by 9. So this is how it will follow. So if I have to write this one in roster form, this one is set builder form, so it will be what? R is equal to 2 comma 1 by 2, 3 comma 1 by 3, 4 comma 1 by 4, dot dot dot, 9 comma 1 by 9. So this is what my roster form is. Now what is the domain? This is the domain for functions. Okay, now here domain is what? Domain is nothing but the set of all the first elements of the relation. 2, 3, 4, 5, 6, 7, 8, 9. Set of all first elements of the relation. So that is of the ordered pairs of the relation. Yes, I missed out that ordered pair. It won't be 1. It will start with 2. How can it be 1? 2, 3, 4, 5, ... 9. So this is my domain. Now the next thing they have asked is what is the range? So range is what? Range is equal to the set of all the second elements of the ordered pairs of the relation, and that is what? 1 by 2, 1 by 3, 1 by 4, ... 1 by 9. That's how we got a domain and range. Okay, so that's how we finish the question. So now we have the third question of the day. So here it's a question of composition. So what we have is, let A is equal to 0, 1, 2, B is equal to 1 half 1 by root 2, 0, and C is equal to this, such that f of A to B and G B to C, where fx is cos pi x by 4 and gy is equal to y square. So we need to find the composition of G of f. Okay, so how should we start this question? So first thing what I will do is, I will try to draw the arrow diagram of the function f and the function g. So what we have of function f is, I write here the elements, it is from A to B, right? It is from A to B. So I will write here A and I will write here B. So the elements of A is 0, 1, 2, and what will be the elements of B? Now listen very carefully. Now when my x is 0, so f0, what is f0? So when the 0 element will be mapped with what? f0 will be cos pi into 0 by 4. So it is cos 0, that is 1. So here comes 1. Achha, let me write all those elements. That will be the elements of 0. Yes, elements of B. Now f of 1 will be what? F of 1 will be, here put x as 1. So cos pi by 4, that is 1 by root 2. Now f of 2 will be what? That is here. If you put 2 in here, what I get? It will become cos of 2 pi by 4. So this becomes cos pi by 2, and that is 0. Cos 90 is 0. So let us do the mapping. So what I get? 0 will be mapped with 1. 1 will be mapped with 1 by root 2. 1 will be mapped with 1 by root 2. Then 2 will be mapped with 0. So this is how we get the mapping for the function f. Okay. Now let us do for the function g. The same thing we'll do for function g. But g is from what to say? That B to C. So let us do it. The function g is from B to C. So here let us write the elements first. So B elements is 1 half 1 by root 2, 0. Then C elements are 1 half 1 by 4, 0, 1 by 8. Okay, let's do the mapping. Now gy is equal to y square. Simple as that. So g1, these are easy. g1 is equal to what? So 1 square, that is 1. g1, now g half is equal to what? G half is equal to half square. So that is 1 by 4. This one will be mapped with this one. Now g1 by root 2 is what? 1 by root 2 whole square. That is 1 by 2. Now 0 square is 0. That's it. So this is how we mapped the function g. So let us write g in here. But we need to find what? We need to find the composition of g of f. So g of f, listen very carefully. So what is g of f? It is a composition of the function f and g. Composition of the function f and g is g of f. So basically what I need to do is g of f, I will write like this, x is equal to, now look at here, what happens? Since f is this size, so I will write g of fx. It will be g of fx like this. Now what are the functions originating? The values in here are what? 0, 1, 2. The function f. The first set is what? A, right? So the elements A will come in here in the values of x. So I will write first element is what? First element is what? Let us write that one. G f of 0. This one is my first element. So first thing I will find G f 0. How much is that? How much is that equal to? Now look at here. Let us do the mapping. 0 to 1. Then 1 to. Acha. F of 0 is what? 1. So I will write here G1. And G1 is equal to what? 1 is mapped with 1. Or else you can see like that. 1, 0 to 1. 1 to 1. Simple as that. Now the next element. Next element is our 1. So G of f of 1. That is equal to what? Now f1 is what? 1 by root 2. So I will write G of 1 by root 2. And G of 1 by root 2 is how much? That is 1 by 2. That is 1 by 2. Now the next element, last element, G of f of 2. That is equal to what? F of 2 is equal to 0. F of 2 is equal to, so G0 is equal to 0. So the composition of G of f is given by, if I write the answer, G of f is nothing but equal to, it will be, what we have in here? It is 1/2. Actually, this is how we write. That's the answer. The composition of G of f is 1. Then we have, so let me write that thing. So composition G of f is equal to 0 comma this element, this 1. Then what do you have? 1 comma 1 comma half. Then what do you have? 2 comma 0. So that's how we find composition of two functions. So we are into our fourth question of the day. So what we have in here is, the function is given by let f is r to r defined by fx equal to x minus 3, and let g be another function that is from r to r, so real function, defined by gx is equal to x plus 3 by 2. So we have to show that f of g, that is composition of g and f, is equal to ir is equal to composition of f and g. So basically, first thing, we already discussed composition in the previous question. Now what is ir? IR means what? It is an identity relation. In R, it is an identity relation. We have already discussed what is an identity relation. So identity relation, suppose we have 1 comma 1, 2 comma 2, 3 comma 3. So this is how identity relations looks like. Okay. So now what we have is, suppose another one. What is the definition of identity? Suppose we have f of gx. F of gx, then that must be equal to x. For identity relation, that must be equal to x only. Then we can say the relation is to be identity relation. So let's start proving this one. First thing, let us find f of g. Let us find f of g first. So f of g x is equal to what? F of gx. We have already discussed in case of composition. F of gx. Now gx is what function? It is x plus 3 by 2. So f of x plus 3 by 2. Right? Now what is the f function? F function, now look at here carefully. Gx I put, it's very easy. Now you look at the function fx. Fx is equal to what? 2x minus 3, right? But we need to find here what? F of x plus 3 by 2. So what I will do, just look at here, just mark here x, underline x in here and underline x in here. So wherever there is x, you just need to put x plus 3 by 2 in there. So what I see in here, 2 into x minus 3. So I will just put 2 into, in place of x I will put x plus 3 by 2 minus 3. Simple as that. So in here, in this fx, I am replacing x with x plus 3 by 2, right? So in here also x, I will replace that with x plus 3 by 2. That's what the function is. Now 2 goes out, right? So what I have in here, x plus 3 minus 3, 3 goes out, we get x. And I told you what? So f of gx is equal to x. So that means what? This is an IR, identity relation is R. Now let's do the next one, g of f. What is g of f x is equal to? So it is what? Now inside we have fx function. Now fx is equal to what? Directly put fx in there. So g of 2x minus 3, 2x minus 3, and that is equal to what? Now, gx is x plus 3 by 2. Gx is x plus 3 by 2. So in place of x, I will replace it with 2x minus 3. So what do you get? 2x minus 3 plus 3 divided by 2. Okay, now let us simplify. 3 and minus 3 goes out. So I get 2x by 2. So I get x again. So what do we see? That again we are getting that g of fx is equal to x. So these two relations are IR. So we can write this one. Since f of gx is equal to g of fx is equal to x, hence f of g is equal to g of f is equal to IR. That's it. Okay, clear? So that's how we solve these type of questions. Understood? So now we have the fifth question. So what is the question is all about? So show that the function f z to z defined by fx 5x plus 3 is a bijective function. So let us go step by step. So what is z? What does this z signify? Z signifies set of integers. So this function whose domain is set of integers and codomain is set of integers, and the function is defined by 5x plus 3 is a bijective function. So first we need to know what is a bijective function. We have discussed this one in our lessons. So bijective function, bi means two. So when a function is injective as well as surjective, when my function is injective as well as surjective, then we can say that the function is bijective function. Now what is injective function? Injective function is a name of 1-1 function. 1-1 function is also known as injective function. And what is surjective function? It is onto function. Okay, and what is 1-1 function? 1-1 function is, suppose if I have, it means I have a function from A to B. From A to B I have a function. So 1-1 function, suppose I am writing 1, 2, 3, 4, 5, 6 in here. So it says that every distinct element, distinct means what? Every different element. Every distinct element of A will have a distinct image in B. So 1 will have the image 4. It cannot have 5. 1 will have 4. 2 cannot have 5. It can have either 5. 2 cannot have 4. It can have either 5 or 6, but it cannot have 4. Same as 3 cannot have 4, cannot have 5. Why? Because 4 and 5 are already acquired by 1 and 2. So 3 can only be for 6. So this is how we have 1-1 function. So a function in which every single element, every distinct element in A has a distinct image in B. Now what is onto function? Onto function is nothing but every element of B must be an image of at least one element in A. So 4 is an image of one element of A, 5 is an image, 6 is an image, onto function. Now if I write 7 in here and 7 does not form any, 7 is not an image of any element of A, then we can directly say that this function is not onto. Okay? So this is how we define 1-1 and onto function. Now in order to do some questions, obviously we will not draw the arrow diagram and we will find, because how can we draw the arrow diagram? They have just shown you the function fx is equal to 5x plus 3. So there is no way we can draw the arrow diagram. So how we proceed with this question? How we prove that the function is bijective? So let us start with 1-1. So what I will do is, now listen very carefully. For 1-1, I am going to do what? I will take two values. I said this one is from Z to Z, right? So I have to write Z in here, set of integers. So what I will do, I will take two elements in here in Z. I will take two elements in Z, and corresponding to these two elements, I have fx1 and fx2. I have fx1 and fx2. This is just for the concept for you guys. How we need to prove one function. So listen carefully. So what I will do, so first thing I will write solution. This one will be let x1 comma x2 be elements of Z. Okay, so I'm taking x1 and x2 are elements of Z. Now listen very carefully. Suppose I say that fx1 is equal to fx2. If fx1 is equal to fx2, so I am saying what? These two are equals. Now listen very carefully. In a set, we cannot have two equal elements, right? So if these two are equal, what I will do is, I have to erase the other one. If these two are equal, I have to erase the other one, right? Now listen very carefully. If fx1 is equal to fx2 implies that x1 is equal to x2, then we can say that the function is 1, 1. Why? Look at here. If I have fx1, fx2 in here, right? So the mapping was like this. The mapping was like this. Okay. Now if I say these two are equal, now if the mapping becomes this one, x1 not equal to x2 and fx1 is equal to fx2, then we can say what? It's not 1, 1. Because two elements have same image. They does not have any distinct image. It is many to one, right? But if fx1 equal to fx2 implies that x1 is equal to x2. x1 is equal to x2 means what? I don't have to write x2 in here. So I'll write just x1 in here, right? So what can I say? This one is a 1, 1 function. So in order to prove a function to be 1, 1, I just need to prove this condition, that if fx1 is equal to fx2 implies that x1 is equal to x2, the function is 1, 1 function. So for the moment, I'm just erasing this one. So please write it down in a notes section for you guys. Important notes, that if fx1 is equal to fx2 implies x1 is equal to x2, the function is 1, 1 function. So from here we have to start. So fx1 is equal to fx2, that's our assumption. So let us say, what is the function? Fx is 5x plus 3, right? So fx1 will be what? 5x1 plus 3. And fx2 will be what? 5x2 plus 3. This is what we have. Now let us simplify this one. So 3 gets cancelled. So we get what? 5x1 is equal to 5x2. Now 5 gets cancelled. Therefore x1 is equal to x2. And once we see that x1 is equal to x2, we can directly say that this assumption we have taken before shows that x1 is equal to x2. Then we can say hence the function is, the fx is 1, 1 function. Is 1, 1 function. Okay, so that's how we prove the function to be 1, 1. Now how do we prove for the function to be onto? How do we prove that the function is onto? Now listen very carefully. For onto, what was the condition for onto? The condition for onto is, suppose we have Z in here and Z in here. Suppose we have an element X in here, X in there, right? And corresponding to this X, there is an image Y in here. Corresponding to that element X, there is an image Y in here. So I will write in here how to proceed with onto function. So let there be an arbitrary value Y in Z. I am taking an arbitrary value Y in Z. This Y in this set, arbitrary value of Y in Z, such that what? You see, y is an image of x. So what we can write? We can write that fx is equal to y. So I am taking one arbitrary value of y such that fx is equal to y. Achha, let me show you one example how we are saying that thing. Suppose I am taking y as 8. Suppose I am taking y as 8. So fx, for what value of x y will be 8? Can I find out for what value of x y will be 8? So what I will do is I will write 5x plus 3 is equal to 8. So 5x is equal to 5. So x is equal to 1. So here I can see the mapping, right? So I'm just taking one particular value of y. Here I have taken 8, but I am taking a general value which represents every single value in integers. So I am representing every single value of z with this element y. So fx is equal to y. You see, fx is equal to 8. So I can write this one as what? F1 is equal to 8. So for the element 1, the image is 8. So in the same way, I am saying that there is y who is an image of x. So what I will do is, now I will write 5x plus 3 now. 5x plus 3 is equal to y. Right? So here I knew 8 and through back calculation I found out 1, right? So now you see I know y, arbitrary value of y. So I know y but I don't know x. So let us try to find x in terms of y. So what I will do, 5x is equal to y minus 3. Therefore x is equal to y minus 3 by 5. Therefore x is equal to y minus 3 by 5. Okay, so this is what we have, right? Now listen very carefully, this one. So looking at this one, what we see is that x is an element. So y minus 3 by 5 is a particular element whose image is y. Y minus 3 by 5 is a particular, now x is equal to this thing, right? So what we found out? We found out that y minus 3 by 5 is the element whose image is y, right? So, and look at here, this y minus 3 by 5, it will always be defined. Y minus 3 by 5, it will be always be defined, right? So since it is always defined, so what we can say is that the function is onto function. So write down. So write down in here. So what I will do is, so for the element y in z, the pre-image, for every, we have to signify for every element. For every element y in z, there is a pre-image. There is a pre-image. This is pre-image. Y, the pre-image of y is y minus 3 by 5. The image of y minus 3 by 5 is y. There is a pre-image that is x is equal to y minus 3 by 5. Hence fx is onto. So that's how we prove that the function is 1, 1 like this way and the function is onto like this way. So at the end we can write is that the function is bijective function because it satisfied the conditions of bijective function, that is 1, 1 and onto function. So now 6th question of the day. Yeah, we are doing so many questions because more questions we do in maths, the most clearer our concepts will get. Okay, so in maths try to practice as much question as you like. And one thing, after solving every question, suppose you get the right answer, the satisfaction which you get, it's hardly expressed. Now let us do this question. So now they're asking the question, just the first line is the question, is g is equal to this a function? That's my first question. If this is described by the formula gx is equal to alpha x plus beta, then what values should be assigned to alpha and beta? So first thing, let us look into the first part of the question, is g a function? So let us start proving that one, that it's a function. So first thing what I will do is, I will try to do the arrow diagram, simple as that. So the arrow diagram, what it does shows, first I will write the first elements 1, 2, 3, 4, 1, 2, 3, 4, and here we have what the second elements 1, 3, 5, 7, 1, 3, 5, 7. Clear? But here they haven't told that G colon from where to where, which set to which set. So let's not write that thing. So what I will do is, let us do the mapping. 1 is mapped with 1, 2 is mapped with 3, 3 is mapped with 5, then 4 is mapped with 7. So now tell me, is this a function? Yes, it's a function. Why? Because the criteria for function is what? Every element in A, let us write this one as A and B. Every element in A must have a unique image in B. That's the criteria for a relation to be a function. So you see, every element does have a unique image in B. It is not having more than one image, right? So every one has one image. So what we can say that this is a function. So let's just write down, since every element in A has a unique image, so for here you write from the arrow diagram. So what do we see from the arrow diagram? So every element in A has a unique image in B, hence what we can write? G is a function. That's it. Now the next thing, if this is described by a relation Gx is equal to alpha x plus beta, so now we have to find the value of alpha and beta. So basically what we see, we need to find the value of two variables, right? Now this is a linear equation. Alpha x plus beta is a linear equation. Now when they're saying it's a linear equation of two variables, how many linear equations do we need to find the value of two variables? I need two linear equations. So I will try to find two linear equations to get the values of alpha and beta. So let us write what are the two linear equations we have in here. So the ordered pairs you see, let us pick the first one, that is 1, 1, right? So here it says when x is 1, gx is 1. When x is 2, gx is 3. When x is 1, gx is 1, right? So when x is equal to 1, gx is equal to 1. Right? And here you see the gx is defined by what? Alpha x plus beta. And that is equal to, I will write alpha, so let me write in here. So g1 is equal to what? It is alpha into 1 plus beta. So I will write this one as equal to 1. So this implies what? Alpha plus beta is equal to 1. So when x is equal to 1, gx is equal to 1. So in place of x, I am writing 1 in here. So this is what we get. Okay. So let me write, no, it's fine. There is no problem in that. Now the next equation. So this is the first equation we got, alpha plus beta is equal to 1. Now let's do the second equation. So when x is 2, when x is equal to 2, gx is equal to 3. This is what we have. So g2 is equal to what? G2 is equal to alpha into 2 plus beta, that is equal to, look at here, gx is 3, so I write here 3, and that implies, that gives us our second equation, that is 2 alpha plus beta is equal to 3. So like this way we got two equations. My first equation is this one and my second equation is this one. So let us solve these two equations, simple as that. How will I solve? I will just do subtraction, equation 2 minus equation 1, and you see what you get, equation 2 minus equation 1. So what do you get? Look at here, let me do it in here. 2 alpha plus beta is equal to 3, alpha plus beta is equal to 1. Now if I subtract, what I get is, this one is alpha is equal to 2. So alpha is equal to 2 we get. If I do equation 2 minus equation 1, so we should have written in here 2 alpha plus beta is equal to 3, alpha plus beta is equal to 1, So if I do subtract, so we get alpha is equal to 2. Now using the value of alpha, let us put in the first equation. Putting the value of alpha in equation 1. So if I put the value of alpha in equation 1, what do we get? 2 plus beta is equal to 1, and that gives us beta is equal to minus 1. So we get, like this way, we get the value of alpha and beta. So here, I hope this is the last question of the day. So enough of problems. Now this is the last. Okay, I hope you guys are tired. You please don't mind, so don't be tired. Let's do this question and with our full concentration. So what we have in here is, consider f r plus 2 this. So r plus means what? Positive real numbers. 2 minus 9 to infinity, defined by fx is equal to 5x square plus 6x minus 9. Show that f is invertible with f inverse y is equal to this is what given. So we need to prove that the function fx is invertible. Now how do we prove that a function is invertible? Now let us see. What I'm gonna do is, first we're gonna write we'll just proceed like the one we have done in onto. So what I will do is, let there be an arbitrary value y. Now that arbitrary value y will be where? It will be in here, because y we are thinking of as image. Y is an image, so it will be here. Let there be an arbitrary value y in minus 9 to infinity. So there is an arbitrary value in there, right? Now in that arbitrary value, so what I will write, such that fx is equal to y. This is what we have. So write this one in here. So fx is what? 5x square plus 6x minus 9 is equal to y. So what we did in previous thing, we tried to express in terms of y, express x in terms of y. So we'll do the same thing in here. But here we see there is a problem. The problem is that there is a square in here. So how will I do it? I hope most of you guys remember that method of squaring. We have learned method of squaring in class 10. So let us apply that method in here. So first thing, let us take 5 common. So if I take 5 common, what we have in here is x square plus 6 by 5x minus 9 by 5 is equal to y. Now take this 5 that side. So we have here y by 5. And what I will do is, look at here. I will try to write this one as a plus b whole square. So I get x square plus 2 into, what is a? A is x into, what should be b such that I get 6 by 5x in here? The b will be what? 3 by 5. Look, 2 into 3, that is 6. 6x by 5. So I get this thing. So my b is 3 by 5. So I will write here 3 by 5 whole square. Okay, now let's remove this thing. 3 by 5 whole square. And what do we have? Now since I've written 3 by 5 whole square, it was not there. I have brought it out. So I need to remove that thing. I need to have an element which can remove it. So minus 9 by 5, which I already have in here, and that is equal to y by 5. So this entire thing what we have is x plus 3 by 5 whole square. So I will write x plus 3 by 5 whole square. Now let us simplify this one. So I get minus 9 by 25, and here we have minus 9 by 5 is equal to y by 5. So how much is this coming? So this one is coming x plus 3 by 5 whole square. Let us take all of them that side. So what we get is y by 5. Now plus, it becomes plus 9 by 25 plus 9 by 5. So plus 9 by 25 plus 9 by 5. So this basically becomes, if I take the LCM as 25, I get 5y plus 9 and plus 45. So we basically get that one as 5y plus 54 divided by 25. So x plus 3 by 5 whole square is that thing. Now whole square, I will take it that side and it will become what? It will become square root. So I get x plus 3 by 5, x plus 3 by 5 is equal to root over of 5y plus 54 divided by 25. So what we have in here is that we will take this 3 by 5 that side. So what we get? So square root of 5y plus 54 divided by, if I take this 25 outside the square root, I get 5 minus 3 by 5, and we have x is equal to, let us write this one together. So we can write this one as root over of 5y plus 54 minus 3. Okay. Now once you see this thing, okay, fine, okay, my answer is done. No, that's not the answer. The question is, we have to prove that the function is invertible with f inverse y. Okay. So for that thing, we need to do something more. This is not the end. So basically what do we get by doing this thing is, I will explain you, wait a second. So by doing this, we got the element whose image is y. The element whose image is y. So basically what we have done is, we had the image y, and we traced back to the element whose image is y, that is root over of 5y plus 54 minus 3 divided by 5. So this element in our plus has the image y in our minus 9 to infinity. Now in order to find the inverse of this function, so I need to what? Switch this one. So I need to switch this thing. So basically what do I need to do is, I need to define a new function. So my new function will be what? It will be like this. It will be, the domain and range will interchange because it's an inverse. So minus 9 to infinity, and it will be to this side, it will be r plus. Okay, so now we have this new function. So let us define the new function. This was the function f. This was the function f before. Now we have to define a new function g, whose element is y, but the image will be root over of y plus 54 minus 3 divided by 5. Whose image is that thing. So let us define that function. Let us define the function. So we will write, let g, the function will be what? Now the domain of the function of g function will be minus 9 to infinity to r plus, be a function defined by, wait a second, defined by gy is equal to root over of 5y plus 54 minus 3 divided by 5. So this is my new function. The element is y, but the image is this one. So this is my new function. Now what you see is, in order to prove that a function is invertible, what do we need to prove is that f of g must be equal to y, and g of f must be equal to x. If these two conditions are satisfied, then only we can say that the function is invertible with, then we can say that the g function is the inverse function of f, and then we can say that the function is invertible with this root over of 5y plus 54 minus 3 by 5. So we need to prove this, both of this. So let us start with f of g. So f of g is equal to y. So first thing, f of g means what? So f of g basically means what? F of gy. F of gy, because gy is the function, it's not f of gx, it will be f of gy. And f of gy is equal to what? It is f of Let's write this thing. gy is that thing, root over of 5y plus 54 minus 3 divided by 5. This is what we have, f of gy. Now f of x is what? Listen very carefully. fx is 5x square plus 6x minus 9. So f of gy will be what? So f of this thing will be what? So wherever there is x, I will put this thing in there. So what we have in here is equal to 5 into, in place of x, I'm putting this one, root over of 5y plus 54 minus 3 divided by 5 whole square. In place of x I'm putting, then plus 6 into x, again this one, root over of 5y plus 54 minus 3 divided by 5. Then we have minus 9. So let us solve this thing. So this is whole square, right? Now we just express this one as a plus b whole square. Let us do it. So what we have in here as 5, the denominator becomes what? 25. The numerator becomes what? Look at here. Let us solve the numerator. Now a minus b whole square. So I get a square. Now a square will be what? Square root and square will go away. I have 5y plus 54. 5y plus 54. Then minus of 2 into root over of 5y plus 54 into 3. Then plus 3 square is 9. Now clear? Now the next thing, plus, just multiply 6 with this thing. So 6 by 5 root over of 5y plus 54. And then what do we have? Minus 18 by 5. Minus 18 by 5 minus 9. This is what we have, right? Now let us simplify. So 5 and this one gets cancelled. So this one is 5 in here. Now let's take an LCM. This problem is getting bigger and bigger. So let us take an LCM in there. So what we have, if I take an LCM of 5, the numerator becomes what? This side is okay. So 5y minus, let us write this thing, 6 root over of 5 by 54, 5y plus 54. Then what we have is 54 plus 9. 54 plus 9 is 63 plus 63. And the same thing, because it's 5 in the denominator, plus 6 root over of 5 was 54. I know it's bigger, but now it will cut. Everything will cut now. So I get minus 18 in here. And I get minus 5 9s are 45. So this is what we have, right? So this one and this one goes. Now you see 18 minus 45, 63. So what we get? Y. So that's proof that f of g is equal to y. Now the next thing what we need to prove is that g of f is equal to x. So we already proved this the first portion. So let us do the g of f portion. So g of f, I know this problem is getting bigger and bigger. G of f is equal to x. Now we have to prove this thing. So for this one, what do we do? G of fx is equal to x. We need to prove this thing. So g of fx, in place of fx, what will I write? In place of fx, I will write 5x square plus 6x minus 9. So I have g of 5x square plus 6x minus 9. Now you see gy is this thing. So g of 5x square plus 6x minus 9 will be what? In place of y, I will write 5x square plus 6x minus 9. So let us do it. So it is square root of 5 into 5x square plus 6x minus 9 plus 54 minus 3 divided by 5, and that is equal to what? Let us multiply. So what we get in here is 25x square, then 30x, then this one is what? Minus 45 plus 54 minus 3 divided by 5. So after this what we have? this minus 54 plus 54 minus 45 plus 54 is plus 9. So what we get is 25. Now 25x square, I can write this one as 5x whole square. This one I can write plus 2 into 5x, 2 into 5x, this is a, and plus 3 square, I'm getting 9 from here. So this is what we have. Now this thing is what? 5x plus 3 whole square. So 5x plus 3 whole square and the square root will go away. So what do we get? 5x plus 3 minus 3 divided by 5. So this goes away. So 5x by 5, we get x. So at the end we can write that since f of g is equal to y and g of f is equal to x, hence the function g is the inverse of f. So what we can write? We have defined the function gy is equal to this thing, right? So in place of g, I can write f inverse y is equal to root over of 5y plus 54 minus 3 divided by 5. So that's how we prove this question. Okay, I hope it's very, very clear. I know this question is very, very lengthy, but it will come for 6 or 5 marks. So don't worry. Step by step, we just have to get to this point that g of f is equal to x and f of g is equal to y. Now, so that's it for today. We have done so many problems. We discussed about the problems of relation and we discussed the problems of functions. We discussed one function, onto function. There's so many things we covered. Then symmetric, reflexive, transitive. So for the next class, we'll be starting a new chapter, that is inverse trigonometric function. So thank you everyone.